Thank you very much. Thank you. And many thanks to the organizers for inviting me. Very interesting program. By the way, Queen Mary and University of London, it's the same. It's one affiliation. So.
But that's the way it looks on the, if you look at the abstracts.
Oh, yeah. Okay. This topic of my talk, the story started about 15 years ago when I worked at Tel Aviv. And at that time, Tel Aviv University Mathematics Department and Computer Science were together. So people like Micha Sharir and Dan Halperin were my colleagues, and this was the result of discussions with them and influenced by them. So it's about robot motion planning and topological approach to robot motion planning, which I will describe in my talk. So my talk will consist of two parts. The first part will be mainly survey, just to introduce the subject and to explain what was known. And the second part will be about some new results, very recent. Some of them are not yet in their final form, so need to be continued. So let's start with motion planning problem. So it's a typical task of robotics. When we have a system, we want it to move autonomously from one state to another. To implement this, we need to have a what is called motion planning algorithm. So this algorithm take as input pairs of states, A and B, where A is the initial state and B is the final state. And the output of this algorithm is a continuous motion of the system starting at A and ending at B. So everybody is familiar with Waze and GPS. So this is a motion planning problem, which is solved by this program Waze, for example. So here state is a geographical position of our car and possibly its orientation on the road. And this algorithm suggests a driving route from the current position to any desired position which we want to go to. So what is a state? I mean, the notion of a state is an important notion, and when we look at a system, we look at variety of its states. So if, for example, I am a system, I am a robot, then my state is not only determined by the position of my center of mass, but also how I'm standing, I mean all these elbows, it's all different states. So state is actually can be characterized by many parameters, many real parameters. So the state of a system is determined by some set of real parameters, let's say some angles, some lengths, some parameters. So we can view a state as a point in some Euclidean space, Rk, and the variety of all states is what is called the configuration space of the system. So it is important to study the configuration space, its topology, its geometry, and many problems of control theory can be even solved without knowing what the system is, but just looking at the configuration space. For example, in this talk, I will discuss this motion planning problem, and we will see how topology of the configuration space is relevant to understand the structure of these algorithms, motion planning algorithms. So let's start with a simple system. So this is robot arm. So it has some bars, some number of bars connected by revolving joints. I assume that it is planar on the plane, so every bar may rotate. So its position is determined by an angle. So in total we have n bars, we have n angles. So the configuration space is n-dimensional torus. And if we are in R3, then each bar has freedom to rotate in 3 dimensions. So it is S2. So the configuration space will be the product of n spheres. Another example is in topology what is called the configuration space. So here we fix some topological space Y, which usually will be just Euclidean space. And we look at variety of placement of n points, n particles in the space Y with no collisions. So we forbid collisions with different particles. So our system consists of n particles moving in a kind of coordinated way inside Y with no collisions. So this is our system, and this picture represents a state of our system. So what is the motion planning algorithm? Just coming back to this notion and trying to express it in mathematical terms. So if X is the configuration space of our system, the motions of our system are represented by continuous paths in our space, so maps of the unit interval into X. This is our motion. So we will assume that X is path connected, which means that we can fully control our system and bring it from any state to any other state by continuous motion. So now a motion planning algorithm, again I'm just repeating what I said in the beginning. We take pairs of admissible configurations as input, and as output we produce a continuous motion of our system which starts at A and ends at B. So now we want to describe it in these terms. So X is our configuration space. X to the I is the space of all continuous paths in X. So it has topology, which is called compact open topology. And there is a natural map, which is called path vibration. So every path is mapped to the pair of its initial and final points. So this is a nice continuous map, which is called path vibration, and it is a vibration in the sense of Serre. So now if we go back to the definition, we see that a motion planning algorithm is a section of this vibration. So it is a map from the base, so it's a map from X cross X to the space of paths, such that if you apply this map and then apply the projection P, you get the initial pair of states. So we just see that motion planning algorithm is a section of this particular path vibration.
Do you want that section to be continuous always?
Well, this is exactly will be the issue now. This is the point here. So do continuous motion planning algorithm exists? So can we have this section continuous? This is this question. And this lemma says that, so the answer is no, essentially the answer is no. A continuous motion planning algorithm exists if and only if our configuration space is constructible. Configuration spaces are essentially arbitrary manifolds, so there is no reason to assume that configuration space which we will need in practice will be constructible. So this means that in real life our configuration space will not be constructible most likely, and therefore we cannot have a continuous motion planning algorithm. So maybe I'll just skip this 2 slides. So in real life, a motion planning algorithm is not constructible. So for example, if my configuration space is some island and in the middle there is a lake, and I want to create a program for the robot to go from A to B, then there will be something like, if it is this side, then go to the left. If something is positive, negative, go to the right. So there will be some discontinuity. So now we want to kind of measure. We want to measure how discontinuous a motion planning algorithm must be. And this is measured by this number, by this invariant, which is called TCX. TC stands for topological complexity of X. So X will be our configuration space. So roughly, this TCX is the minimal number of continuous rules which you need to describe any motion planning algorithm in X.
This is like the number of partial sections, continuous partial sections.
It is the number of, yes, it's exactly next slide, there will be definition. So it is a number of, it can be characterized in several different ways. One of them is the number of locally defined continuous sections with domains, let's say, covering the whole variety, or we can say with domains partitioning the whole variety, which I prefer, I will use on this slide this definition. So I'll say that a motion planning algorithm S is tame if we can split the whole variety of pairs X cross X into K+1 sets, which are disjoint, which are all pairwise disjoint. And this algorithm, if you restrict it to each of the sets, is continuous. And there is a technical assumption which says that each of these sets must be Euclidean neighborhood retract. So it cannot be some exotic space. So algorithms which appear in practice, they all of this type, because usually the configuration space is a semi-algebraic set, and these sets Fj are also given by certain polynomial equalities and inequalities. So they are also semi-algebraic, and therefore they are Euclidean neighborhood retracts, and the functions which implement the functions which implement motion planning, they are usually also given by some analytic functions, so they are continuous. So now I want to define this. On this slide, I want to define what is called TCX. So maybe I'll start with the second definition. The topological complexity of a path-connected topological space X is the minimal topological complexity of motion planning algorithms. It should have said of tame motion planning algorithms. So it should say tame there. And topological complexity of a tame motion planning algorithm is this minimal number k, which appears here. So the minimal number of domains you need to subdivide. So this is a definition. I mean, you can say, definition, as a definition, it's fine. But what is surprising, actually, what is nice here, is that this number is a homotopy invariant of X. So it depends only on the homotopy type of the space, which is very important because you can use algebraic topology, cohomology, and everything we learn in topology to compute this number. And we will see that it is actually quite helpful. The second property is actually repetition of what I have said before, this lemma which we had before. It is 0 if and only if X is contractible. So 0 means that there is only one domain. So it means that you don't need to partition. So the whole, there exists a globally defined continuous section. And the third property says that there is an upper bound for the topological complexity, which is dimension of X cross X. So, I mean, this is also very important because suppose I am looking at some practical problem, and suppose dimension of my configuration space is, let's say, 5. So then this will be 10. So the complexity will be at most 10. So for computer science, it's not a big deal. So there will be 10 sub-programs. But if I have a situation where the dimension of my space is large, then I indeed may have complexity. We will see many examples now that this TC actually, in many situations, it equals this dimension. So then in this situation, we will have a motion planning algorithm with many sub-programs.
Which dimension is this?
Well, this is covering dimension, but let's assume that X is always simplicial complex, and yeah, but it is covering dimension. So let's look at an example here. So we, suppose our configuration space, is a circle. For the pendulum, it is a circle. So we have 2 points on the circle, A and B, and we want to move from A to B in a continuous way. So what we can do, we can say, we can look at set F0. This will be all pairs A and B such that they are not antipodal, like on this picture. So if A and B are not antipodal, we can just move from A to B along the shortest geodesic arc, and this is a continuous section. So this will be our first set, F0. And then remaining set, F1, will consist of all antipodal pairs. And here, to create a continuous section above this set, we can say, we can fix some orientation on the circle and say we go from A to minus A in that direction. It's also...
when you defined this, you didn't ask that F will give you the shortest path.
No, no.
So why here I cannot say that I will always go clockwise, and that will be a continuous?
But it will not be continuous.
Why?
Well,
Because A to A, right? That's the problem.
But A to A, you don't assume that
no, Alex.
is not equal to B?
Well, it will not be continuous. For example, if it will be not, for example, here, if I have a, John, let me just answer. So if I have this pair, if I move it slightly in this way, shortest path will go that way. And if I
No,
move
understand,
this,
but you didn't ask that you want F to be the shortest. That's what I
Oh, yeah, I didn't ask. But anyway,
No, he asks what about the rule that says always go from A to B clockwise?
well, this is also not continuous.
Okay.
How do you go from A to A?
Yes,
Right?
exactly.
That's the question.
Yeah, I mean, there is no continuous because circle is not contractible. I mean, by that lemma, the circle is not contractible. So, but here we have an algorithm with two sets. So we see that TC is less or equal than 1, but it cannot be 0 because the circle is not contractible. So now let's look at this next example. Just a moment. Okay, so this is my next slide. So this is similar example. Suppose again now my X is a sphere of odd dimension. I can do the same. I can say F0 will be pairs of not antipodal points, and F1 will be the set of pairs of antipodal points. And now I have to specify how to go from A to minus A in a continuous way. And here I can do the following. Because I assume that dimension is odd, I can fix a non-zero tangent vector field on the sphere. And then I can say I follow this geodesic which goes from A to minus A, which starts in the direction of this vector field with velocity vector v of A. So this again shows that TC of any odd dimensional sphere is 1. So now let's look at the next example when we have even dimensional sphere. So this argument doesn't work. So we can also say we take F0 the same as before, the set of not antipodal pairs. Vector field, we don't have such a vector field, but we may assume that it is non-zero everywhere except a single point. So there is a single point A0 where it vanishes. So now I can define F1 as before, but here I assume that A is not that point. And now I add an extra set consisting of a single pair. And this shows that TC of odd dimensional sphere is less or equal than 2. And we will see actually it equals 2. So to show that it actually equals 2, so we need some cohomological technique here, which is useful in many situations. So I fix some field K. And I look at cohomology with coefficients in this field K. It is a graded algebra. And this multiplication, this cup product is multiplication. So I can also view this as an algebra. The tensor product, I can make an algebra using this multiplication, which is shown here. So we multiply tensors, and there is a sign coming up here when we interchange V1 and U2. So this makes this tensor product an algebra, and then this cup product becomes an algebra homomorphism. So what we want to look at the kernel of this cup product. So just go back to the slide. So I just said that this is an algebra, this is an algebra, this is algebra homomorphism. So the kernel is an ideal. The kernel of this map is an ideal here. So this ideal is important. So we call it ideal of zero divisors. And next, so we have this ideal, and now we take products of elements of this ideal. And we call the zero divisors cup length is the longest product of elements of this ideal which is non-zero. And the theorem, which is not a difficult theorem, says that TC, this topological complexity, is always greater or equal than the zero divisors couplings of this cohomology algebra. So to apply this, we need to look at the cohomology algebra and to see how, well, what are the zero divisors and how many products we can get of non-trivial zero divisors. Okay. So let's look at this example again, this even-dimensional sphere. So cohomology algebra of sphere is very simple. I mean, there is one generator in degree n. There is one single generator in degree n. And of course, u square is 0. Now, if you look at this tensor, you see 1 tensor u minus u tensor 1 is a zero divisor. Because if we apply product, so we apply product meaning that instead of this tensor, we multiply them. So when we multiply them, they cancel each other and it is 0. So it is a zero divisor, which is good, But now, we want 2. We want 2. So we want a square. We look at the square. We look at the square, and now we use that this n is even, this degree of this class is even, so we calculate the square using that formula which I showed on the previous slide, and we see that it is this tensor, which is non-zero tensor, so it's non-zero. So we see that TC is greater or equal than 2, but we also know that it is less or equal than 2, so it is 2. So we see this, that topological complexity of spheres is 1 if dimension is odd, and 2 if it is even. So now I want to show you some other calculations. I will not do any proofs, but just to show you the results. So if we have a graph, X, connected graph, TC is 0. If it is a tree, if the first Betti number is 0, it is 1 if it is homotopy equivalent to the circle, and it is 2 if the first Betti number is bigger than 1. So for any graph, I mean, maximum you can get is 2. But by the way, 2 is the dimension of x cross x, so it is it's kind of generic situation. Surfaces. If you look at a compact orientable surface of genus G, then TC equals 2 if genus is 0 or 1, and then it becomes 4 if G is greater than 1. And 4 is again a dimension of x cross x. If we look at a group of orientation preserving isometries of R3, rigid motion, group of rigid motions of space, TC equals 3, and more generally, for any Lie group, for any topological group, TC actually equals the category. And in fact, it is true that for any H space, it's also TC. Cat of G is Lusternik-Schnirelmann category, which should I?
Maybe if you can say in one sentence.
Yeah, it is in one sentence, maybe in 2 sentences. So it is a very similar invariant to TC, and it is classical invariant, which was initiated maybe 80 years ago, something like this. So it is. So we have a space X, and we cover it by open sets such that each of the sets is contractible in X. So each of the sets can be homotoped to the base point. So it is similar. What is the similarity here? So in the case of TC, we cover X cross X, and we don't want the sets to be contractible to a point. We want them to that there exists a section of this vibration.
Presumably they gave a lower bound for periodic orbits in terms of this quantity in Hamiltonian mechanics. Isn't that what they were doing?
You mean TC, category? Yeah,
Yeah, this number probably was an invariant for which they could give lower bounds. They were looking for periodic orbits in Hamiltonian mechanics.
Yes, it is used in for periodic orbits and for critical points. I mean, original Lusterning-Schliemann category was for critical points of functions, and of course it is used in Hamiltonian dynamics.
I'm assuming that that number is a lower bound usually. It's useful to know it's big.
Yes, yes, exactly.
You
Yes.
want to know it's small, they want to know it's big.
Okay.
Is there a general connection between TC and the category?
Yes, there are inequalities. I mean, they don't. Let's see. I have a check. So TC is greater than TC of X is greater than category and less than category of X cross X. So there is this interval, yeah, and it may vary. I mean, it.
So both inequalities are...
Yeah, both inequalities, and there is no further kind of restrictions for them to.
Category is always smaller when you put the dimension.
Yes, category is always smaller than dimension. Okay, so more examples. Robot arm, as before, the first example. So for the robot arm, we have a configuration space is a product of circles, a torus, and TC is n. And when n is the number of circles here, and if in the spatial case we have product of n spheres, then it is 2n. So here you can see, for the first time, you can see that complexity can be large. It is actually proportional to the number of degrees of freedom. Yeah?
Are there examples where, for generic choices of points, I can't have a plan which works almost always, and because you have the antipodal point, which is very special and so on. So suppose my algorithm is just wiggle the beginning and end points, and then have, is it possible to have just one movement?
Well, algorithm for this, yes, always, you can always define a continuous section on some open dense set. This you can do, but it will have many instabilities in this sense. I mean, they will. You can do it. Yeah. So this is another example. I'm just looking at. Oren, when do I need to finish?
You have till about 13 after the hour.
Okay. So, so this is when we have configuration space of n particles in RD, n distinct particles in RD. So we want to move one configuration into another without collisions. So the complexity in this case is also proportional to the number of particles, and it is 2n minus 3 for the planar case, and 2n minus 2 for the R3 case. And the same is true for, let's say, any D, any even dimensional D, and any odd dimensional D. So this sounds good. Just last example is about real projective space. So we want to create a motion planning algorithm for real projective space. So in practice, we look at lines through the origin in Rn plus 1, and we want to rotate, move one line to another. So what is TC of RPN? So actually this is a critical example because for the category, it's very simple answer. Category is n. But the answer which we got with Tabachnikov and Yuzvinsky is the theorem says that for n distinct from 1, 3, 7, this number is exactly the smallest integer k such that the real projective space can be immersed into Rk. And for the special numbers 1, 3, 7, this number is exactly n. So this was a little bit a surprise for us. And this, just to explain what is immersion here, immersion is a smooth map such that differential is injective at every point. And this well-known Whitney immersion theorem says that any n-dimensional manifold can be immersed into Euclidean space of dimension 2n minus 1. So this follows that Tc must be less or equal than 2n minus 1. And in fact, it is equal to 2n minus 1 when n is a power of 2. So on this slide, I show that this number Tc of Rpn, this number Tc Rpn, as function of n. So I just want to say that it is not known general formula for immersion dimension for real projective spaces. Also, it is known until at least until 23 and further. There's many series of integers for which it is known, but there is still no general formula. So you can see here, let's say powers of 2. Let's say 2, then it will be 2n minus 1. 4, it will be 7. 8, it will be 15, and so on. So this is this result. Okay. Okay, so now this was my first part of my talk, so it was about survey part of my talk. So, so now, most recently, we were thinking about spherical spaces and how to express the topological complexity of spherical spaces. So a spherical space is a space which has no homotopy groups except the fundamental group. So all high homotopy groups vanish. So it has only fundamental group, and all homotopy group depends on this fundamental group. So we obtain that, so we obtain that if for in a spherical space, the topological complexity is just a function of the group. And we want to know how to compute it algebraically. So this can be compared to the Eilenberg-Burgener theorem, which expresses the category, the Lusternik-Schnirelmann category of spherical spaces, and it says that it coincides with the cohomological dimension of the group. So, I mean, what we expect here is to get an algebraic invariant of a group of this kind of topological cohomological dimension. Okay, so if we look at the examples, let's say if we look at Zn, Tc equals n, and cohomological dimension of Zn is n, and Zn cross Zn is 2n. So you can see in this example, Tc equals cohomological dimension of the group. But if I look at the free group on any number of generators bigger than 2, then Tc equals 2, and cohomological dimension of f cross f is 2. So in this case, Tc equals cohomological dimension of group cross group. And also for the surfaces, we see that Tc equals 4, and it is cohomological dimension of pi cross pi. So we see in some cases we have one behavior, in some cases we have different behavior. So I want to state two theorems. So for the first theorem, I need to introduce some notations. So this first theorem will be dealing with equivariant topology, equivariant CW complexes. So let G be as a discrete group. A G CW complex is a CW complex with left action, with left G action, such that for each open set and each element of the group, such that the shift of this action of this element on the cell intersects the cell itself, then the left multiplication by G acts identically on this cell. So essentially there is a property that the group acts on cells moves cells as a whole. And now we also need to fix a family of subgroups of G. Well, let's call it F. And this will be a set of subgroups which is closed under conjugation and finite intersections. So with these two notions, we want to define what is called classifying space, classifying G CW complex of G with respect to a family of subgroups. So it is a G sub, so everybody knows what is usual classifying space, but now we have with respect to a family. So which means that we allow actions which are not free, but it have isotropy controlled by this family. So we have we call G CW complex EFG. We say that it is classifying complex if it has the following two properties: that isotropy of every element belongs to this family, and it has this universal properties that for any other G CW complex with the same isotropy, there is a unique map into this classifying space. So these two properties define uniquely what we dealing with. These are called classifying complexes with respect to families. Maybe I'll skip this one. So what we will be for this motion planning problem, we will take as G the product pi cross pi, and as our family of subgroups, we will consider all subgroups of G which are conjugate to the diagonal and all intersections of conjugates of the diagonal. So it is a kind of smallest family generated by the diagonal. So this theorem is a joint work with Mark Grant, Greg Lupton, and John O'Prea. And it says the following. So maybe before I start the theorem, I just want to say, so we have G, this our group, G is pi cross pi, and this is this classifying space with respect to this family which I defined earlier, and this is the classifying space with no family for free actions, so you can say it corresponds to the family consisting of the trivial subgroup. And there is a canonical map here. Canonical map unique up to equivariant homotopy. So we claim that this number Tc of pi is the smallest dimension k, such that this canonical map can be factorized through through some L G CW complex of dimension k. So essentially it is kind of dimension of this map, this dimension of this canonical map. So pi is a given group, so pi is given group, and G is pi cross pi. So, how much time do I have?
About 10 minutes.
10 minutes. Okay, good.
No, you have less than 10. You have about 6 minutes.
6 minutes. Okay, so I'm just thinking.
If you ask again,
Ask again.
So, I mean, so this theorem, I just want to say, this theorem says that this number equals. So it's characterization of this number in some, not really algebraic, but homotopy terms, equivariant topology terms. I mean, it would be nice to have it purely algebraic, like cohomological dimension, which we will see in a moment. So it has two, can be used in two ways, to get upper bounds and to get lower bounds. So to get upper bounds, we can just say that using the theorem, this TC is less or equal than cohomological dimension of pi cross pi with respect to this family. And this 3, let's ignore this 3 for now. Maybe I'll skip this Bredon. I will skip Bredon cohomology for now. Okay. Yeah, I'll skip this part just because I think I'll be over time and I want to go to this. The second second main result is the theorem. So in this theorem, what is good that we give a precise answer, well, more or less precise answer, but it is restricted to the class of hyperbolic groups. So, so this is a joint work with Stefan Mescher, and it says that if pi is a finitely presented torsion-free hyperbolic group, then TC of this group equals either cohomological dimension of pi cross pi, or it is one less. And in all these examples which I showed you, when we had a hyperbolic group, the TC was equal to the first option, option A. It was equal to cohomological dimension of pi cross pi, except one case. So that we have only one example when the second option takes place. It is the case of pi equals z. So it is actually the only abelian hyperbolic group. And we suspect that
You don't know which of those two happened.
we do well in
If I
some.
give you something.
Depends what you give me. But well, in many examples we have, as I said, in all examples when we know the answer, it is the first possibility. The only example when we know the second option takes place is Z. So we actually expect that it is Z is very special case. So we think it is possible that it is the only example. So the proof of the second, how much? 3 minutes. So just to make a few comments about the proof. So the proof is algebraic, and it uses some homological algebra. So we look at augmentation exact sequence, and we equip pi with a bimodal structure using this action on left and the right. So it is this exact sequence of pi cross pi modules, and it defines a cohomology class V, which we call the canonical class. So it is a twisted cohomology class of pi cross pi with coefficients in the augmentation ideal. So this class is really important. So what we know that if some power is non-zero, if some power of this class is non-zero, then TC is greater than n. So I mean the main question is to check how do you check that some power is non-zero. So what we have actually, it is a spectral sequence. It's a nice spectral sequence, exact couple, bigraded. So these are the initial term of D0 is just usual cohomology, and other terms are just some x's, some higher x's. And what we so maybe I'll just go to the next slide. So what we observe that this E term, the initial term of the spectral sequence, can be computed very explicitly. So we showed that this E term, E0 RS, can be expressed through this X, and then it can be decomposed as a product of cohomology of centralizers of action. So we have an action of G. So G acts on this S tuples of non-trivial elements by conjugation, like here, and this C prime is the set of all orbits of this action. So for each orbit we have a normalizer or isotropy of this orbit, and this theorem expresses the E terms through cohomology of these centralizers. So knowing this, we can say that for hyperbolic groups, these normalizers, they are always trivial or Z, cyclic. So this shows that in the case of, let's say, torsion-free hyperbolic group, this E term will be 0 for all R greater than 1 and for S greater than 1. And so using this, we prove that theorem. So I think I'll finish here.